yes? Test. All right, let's begin. Our next speaker is Jared Weinstein. Take it away.
Hey, how about now? All right, well, it's my distinct pleasure to be here at Arizona Winter School. You guys are all very, very lucky. This is my fourth winter school. I have to say it was a crucial part of my development as a mathematician to be here as a graduate student. It was the very first time I ever spoke at a conference. It was 5 minutes, and it was at the end. It was on the last day, so some of you will have that privilege when you work on the projects. For the graduate students here, the people that you will meet this week may well be the colleagues that you will have for decades. So get to know the people sitting around you. It's very, very important. And it's just a lovely place. It was, I have to say, about the time I was graduating, being at the Arizona Winter School, it played a role in my decision to stay in mathematics. And here I am today speaking to all of you. It's wonderful. So, I'm going to talk about Adic spaces. You know, if maybe you've already bought the fact that perfectoid spaces are important, despite their failure, as Peter says. But to understand perfectoid spaces, you need to understand Adic spaces, the geometric framework on which they rest. So the category of perfectoid spaces, I'll put it right here. It exists as a full subcategory of the category of Adic spaces. So we'd better find out about those. And Adic spaces are wonderful. They contain multitudes. Here I can embed schemes. Well, the little asterisk I'll explain later. Formal schemes. Rigid spaces. And if you've heard of them, Berkovich spaces. Can be placed inside of a common framework. And that framework, which is Adic spaces, so they're due to Huber, and they blend aspects of algebraic geometry schemes with analytic stuff like manifolds. You can talk about epsilon neighborhoods like Peter was talking about. What are Adic spaces? Well, they themselves can be described as kinds of ringed spaces. It's a ring, it's a topological space together with a sheaf of rings. And you already know of schemes in this context. A scheme is a kind of ringed space which has a model space, which is the spectrum of a ring. And so many categories that you already know are like this. Manifolds of whatever sort, continuous, differentiable, smooth, symplectic, whatever, or complex, analytic, spaces. Oops. These are all kinds of ringed spaces, right? For each of this, you say, I'm going to define a manifold, a complex analytic space, whatever, a scheme. It's going to be a ringed space which locally looks like blah-bitty, blah-bitty, blah, right? A model space. So we have to describe what the model spaces are for the category of Adic spaces. They are going to come from rings. Those rings are called Huber rings, but more on that in a second. So actually, I'm going to begin talking about rigid spaces. But very briefly, because we're going to be passing to the more general Adic spaces very shortly, I'm not going to define these in generality or anything. Go to the notes, or for this, you can go to 2007's Arizona Winter School Notes by Brian, right? Which were all about these. And I'm just going to say, so in the world of rigid spaces, you want to give good meaning to something like the rigid unit disk, and that's the most basic example. So let's just talk about the rigid closed unit disk over QP. So this is just an example. And, right, so let's define a ring, QP angle brackets T, right? This is the first sort of ring you learn about in the theory. And this is supposed to be the ring of p-adic analytic functions on the closed unit disk. So it's going to be power series which converge on that disk. And, the non-Archimedean world is so nice. The test for convergence on that disk is just that you want the coefficients to just go to 0. That's good enough, right? So this converge on t less than or equal to 1, right? And so the model spaces in the world of rigid spaces are built out of rings like this. This is called a Tate algebra. You learn about general Tate algebras. You could adjoin many variables rather than just one, and then mod out by whatever ideal you like. That's a general affinoid algebra over QP. And then where does the model space come from? Well, you have to turn this into a topological space. How do you do it? Well, in the world of rigid spaces, you take the maximal spectrum. So let me let X be the max spec, SPM, right, of this ring. Okay, so you learn a bit about this ring, and you learn that its maximal ideals, they're principal. They're all generated by elements f of, oh, not x, t, that's my variable, t, and in fact, you can take f of t to be a polynomial, if you like. And the max spec of this, you could just relate it to roots of the polynomial f and form a bijection between this set and the set of all elements in QP bar, right? Where the absolute value of x is less than or equal to 1, except you get the same element if you're in the same Galois orbit, so we'd better mod out by the action of the Galois group of QP, right? Okay. And so we have a bijection of sets here. All right, so what do we do to get our model space? We need to take X and put a topology on it. On this X. And this topology is going to have all sorts of desiderata. What do we want it to do? It's supposed to be the space of functions on this X. Well, the space of functions on X had better be related to A. So one thing we definitely want is that the global sections of the structure sheaf should return this ring of functions A, right? But we immediately run into this problem, which is that the space X, if you give it its kind of native topology coming from QP bar, that's totally disconnected. And so if we try to form this, the thing is you could just cover X with Clopin sets any way you like and take a locally constant function, and that will be a section of this. But then that's not really captured by this A. So if you have X be its native topology, you get many more functions than you bargain for here. You need some kind of way to rigidify the situation so that there aren't as many functions, which means you need to maybe have X be connected. The closed disk should really be connected. So how do you do this? Okay, so I'm going to put this here. And the rhythm of this is that I take a new piece of paper. Okay, put a little part 2. And the problem is that the native topology is totally disconnected. Okay, is it visible? Yeah. And the solution to this, due to Tate, well, it's just to change the topology. Although Tate's solution is not a literal topology on the set X, it's a Grothendieck topology. G topology. On X, with admissible opens and admissible covers. So it's some kind of restriction on what kinds of opens in this set X there are and what kinds of collections of opens constitute a cover. And I'm not going to go over this. You can check the 2007 Arizona Winter School notes or many texts on the subject. But just as an example, the sort of thing that might disconnect X is a set like this. So here, I'll do a set of all elements T which are less than 1. And the set of all elements T which are equal to 1. Okay, these are both open subsets of our set X. But certainly everything in X is either less than 1 in absolute value or it's equal to 1 in absolute value, right? But this does not count as an admissible cover. there's some finiteness condition that comes along with admissibility, and that's not satisfied. Essentially, the problem is here. That admissibility condition is stated in terms of affinoid or rational subsets, and essentially the problem is it takes infinitely many rational subsets to fill up this whole open disk, right? And so, as a result, X can't be disconnected this way. Although it points to a funny part of this theory. I can let Y be this. And I've written Y equals X, and that's true as sets. But in the category of rigid spaces, these two are not isomorphic. You have a map from Y to X. This is a bijection on points, but not an isomorphism. Okay. And so that's a wee bit strange. I mean, rigid spaces have had many, many successes over the years. They're perfectly fine to work with, but this is slightly strange, you have to admit. And there, in the notes that I wrote, there are other examples of this. You can take X and delete a kind of transcendental point from it, and then what's left is this rigid space Y, and Y and X have the same points, but they're not isomorphic, right? And there's even other stranger things you can do with this. So this is pointing to an issue that, as a practical matter, X doesn't have as many points as it should. And so there's a way to rectify this by adding more points to X. Okay. And so that's one problem with rigid spaces. Another kind of problem is that, well, I don't know, maybe this is too nitpicky, but the scope is too narrow. With rigid spaces, you have to choose in advance a base field, and then you talk about the space of the category of rigid spaces over that base field, and the field must be a non-Archimedean field. It is not allowed to be a ring like ZP. There's no ring, there's no Tate algebras over ZP, and there's no rigid geometry over ZP, and you want to work with integral models a lot, like Peter's introductory talk made reference to integral models, and there's just no way to talk about them. So just as a very basic example, there's no way you can talk about, so I'm putting this in quotes because it doesn't make any sense, but you can certainly go ahead and write down a ring ZP angle brackets T. So power series with ZP coefficients that go to 0. That's fine. That's functions that are bounded by 1 on QP, on the closed unit disk. And this should be fibered over spec ZP, which should be a 2-point space, spec ZP. There should be a special point and a generic point inside of spec ZP. And there should be a special fiber and a generic fiber of whatever this is. And the generic fiber should be what should the generic fiber be? So the generic fiber should be spum QP angle brackets T. So there's there's no way to talk about this here. And the thing is, you can actually do this. There is something called a Raynaud generic fiber, which takes a formal scheme over ZP and does exactly what you want. And there's even fancier things you can do. Well, I could have put a power series ring here instead of angle brackets T, and then the thing that you expect as the generic fiber should be the open unit disk, things that are strictly less than 1. But in the world of rigid spaces, there's no language for this. Okay, so that's one other mild criticism of it. Okay, so these are the problems that are going to be addressed by working with Huber's theory of Adic spaces. To an extent, some of those problems were already addressed by Berkovich's theory. I will make some mention of that later. So this goes here, this goes here. Great. Three. All right, so I want to loosen up the theory of rigid spaces a little bit. I don't want to necessarily work over a fixed field like QP, but I want some kind of topological ring, and that class of topological rings is called Huber rings. Basically, the layout is I'm going to introduce this class of rings, and then define a topological space attached to each one, and then declare the category of Adic spaces is ringed spaces which locally look like they come from Huber rings. So, all right, what classes of rings are allowed? So, here we go, definition. Well, they're topological rings. A topological ring A is called Huber. And I should say an alternate term that Huber himself used was F-adic, where F, I think, stands for finite. Is that right? If there exists an open subring A0, the subring is called a ring of definition. And the topology on this A0, this open subring, is supposed to be linear and generated by an ideal I. So I'll just write whose topology is I-adic for a finitely generated ideal I inside of A0. And that ideal is called an ideal of definition. Okay. And this is general enough to do a lot of things that we wanted to do. So let's start doing this. So one remark is that the ring is Huber if these other structures exist, but those other structures, the ring of definition and the ideal I, are not included in the they're not included in the data of A. You could have different A0s for a given A. Okay. So here are some examples of all of these. Okay. So the first example is any ring whatsoever with its discrete topology. And so when I said that Adic spaces contain schemes, well, there is an asterisk there, but this is what I meant. You can give any ring R the discrete topology. And then what's A0? A0 can be R, and what's I can just be the zero ideal. One bullet point. Okay, next example will be the field QP, or any p-adic field, or any non-Archimedean field whatsoever. And it's the A0 there. So an open subring, whose topology is generated by an element, or so by an ideal. So how about ZP? And then the ideal can be P, right? So the ideal generated by P generates the topology in ZP. And in fact, ZP is complete for that topology, and ZP is contained as an open subring in QP. It would not be good to have A0 be all of QP. That wouldn't work, because P is invertible in QP, and so the ideal it generates is the unit ideal, which gives you the wrong topology on QP. So that's why it's important to have this moving target, this ring of definition here. Okay. Next example would be this Tate algebra, the one I just mentioned. Okay. So here, what's the ring of definition? Well, a perfectly good ring of definition might be, oh, by the way, I mean, this ideal could have been P squared, right? That also generates the topology all the same. Fine. ... A0 could be ZP, angle brackets T, right? And the ideal here, well, what generates the topology on this ring A0? How about just P? That works just fine. In fact, this A0, it's not so far from being a polynomial ring over ZP. This literally is the polynomial ring ZP brackets T, but I've completed it with respect to the topology induced by the ideal generated by P. That's all that this thing is. Then when you invert P, you get the full ring here. So this is a Huber ring as well. What else? There are so many. So let's take any ring whatsoever, right, with its discrete topology. And let's take a power series ring in finitely many variables. And this is a Huber ring. So if I let this thing be A, what's my what's my open subring? It could just be A itself, right? So this can happen as well. And A0 being A, the thing is the topology here is generated by the elements T1 through Tn. So I could be T1 through Tn. Or it could be the ideal generated by the squares of those elements, or it could be the square of that ideal, or infinitely many variations along those lines, okay? So this generates the topology on this. And you could also do ZP. Double brackets these things. That would be fine Same story with the ring of definition, but this time the ideal. Right, I don't want to ignore the p-adic topology on ZP, and I have to just make sure that powers of p go to 0 in this ring. So the ideal really should include p. That's what this is. I mean, if you think about it, this ring is power series in n+1 variables. One of those variables is p itself. And then I guess the last one, last example is a little bit strange. It's something like if I replace p with something else. So let's suppose K is a non-Archimedean field like QP, but I'm going to demand that it be perfect of characteristic P. Okay, so it's an ultrametric field in characteristic P, and I'm demanding that it be perfect. Actually, this is a perfectoid field in characteristic P. That's all they are. And what I can do is take its ring of integers, okay, and I can consider its ring of Witt vectors. This example is going to be kind of important later. So if I have a perfect ring, any perfect ring whatsoever, I can form the ring of Witt vectors. That's going to be power series in P with coefficients labeled by elements of whatever's inside that perfect ring with some complicated addition and multiplication laws, right? This is a topological ring. It's its own ring of definition. And the ideal will be generated by P is one generated, but there's going to be another one. I don't want to forget the topology on OK. And so I include it by including the Teichmüller representative attached to some element inside of OK, which is less than 1 but non-zero. Okay, such an element is called a pseudo-uniformizer of K. Okay. So here the ideal of definition has two elements. Is when did I begin and when do I end? Okay, so I end 11:20, 11:10? 11:10, okay. So this goes here and this goes here. Great. All right, well, we have a few more vocabulary words to go through. So Huber rings, there are many, many Huber rings, but there are some which are particularly nice, and in the world of perfectoid spaces, you exclusively focus on certain kinds, and those kinds are called Tate-Huber rings. Sorry, Tate uniform rings. So there's two more words here. So, okay. Say, given a Huber ring A, but A0 in A be the subring. This is an upper zero, or upper circ, of power-bounded elements. All right, this notation came up in Peter's talk. For a Banach algebra A, this would indicate the elements which are bounded by 1. If there is no Banach norm on A to begin with, what am I doing? I have to come up with the concept of boundedness, which you can do in any topological ring, and then you can form the ring of elements, the subset of elements, A upper 0, for which the powers of that element form a bounded subset of A. So this is explained in the notes. If A is a Huber ring, then A0 is going to actually be a subring of A. So even without A being a Banach algebra to begin with, you can form this A0. Well, that's not a precise definition, but this is true, for instance. Okay. And, definition. A is uniform. So this is one of the words that came up in the last talk. If A0 itself is bounded. It's a bounded subset of A. Okay. Uniform rings are rather nice. I'm just going to give you an example of one that's not uniform. So if I look at the ring QP, just polynomials in T, but then I'm drawn out by T squared. So dual numbers over QP, and I'm going to topologize this. I mean, it's a two-dimensional vector space over QP, so that's its topology. And then which elements are power bounded? Well, they have to have ZP as their constant coefficient, but then the coefficient of T can be anything. because t squared is 0. So this is not bounded because it escapes any compact subset that you like, right? It has elements p to the minus nt, and that goes off to infinity. Okay, this is not uniform. Okay. All right, so that's uniform, and the other adjective we need is Tate. If it contains a special element, which is topologically nilpotent, unit. It contains a topologically nilpotent unit, and such a unit is called a pseudo-uniformizer. When you think about p-adic fields, a p-adic field contains a uniformizer, something of absolute value 1 when you normalize that absolute value, and or valuation 1, and it is a unit, of course, because it's non-zero, and it's topologically nilpotent because it's less than 1, so we're just taking those two things and abstracting them to general rings, general Huber rings. So a Huber ring is Tate if it contains such a pseudo-uniformizer. So these two things are in tension. Being topologically nilpotent, your powers go to 0, but you're also a unit, meaning you're invertible, so these two things are in tension. And once you contain such a thing, if you are Tate, that actually puts a very strong condition on what your topology is. It essentially all comes from the pseudo-uniformizer, in the way that P really defines the topology on QP. So rather than having elements T1 through Tn generate your topology, just one element generates your topology. That's why it's nice to be Tate. Okay. Uniform, these two adjectives together are nice. Uniform Tate rings are nice. And I'll just, not to give away the game, but perfectoid algebras, from which we will get perfectoid spaces, they're all uniform Tate rings. Okay. So uniform Tate rings are nice. Why are they nice? If I could just take A upper 0, the ring of power-bounded elements, these serve as a ring of definition. With ideal of definition generated by pi, where this is a pseudo-uniformizer. All right. So what are some examples of rings which are both uniform on Tate? QP itself, QP angle brackets T, because its power-bounded elements is this, and that's bounded. That's nice. What's not uniform Tate? Well, here's something that's not uniform. What's not Tate? Well, ZP is not Tate. Anything which is topologically nilpotent has to be divisible by P in this ring, and then it's not a unit. Yeah? Or this sort of thing I was talking about before. Okay. These elements T1 through Tn, they're topologically nilpotent, but they're not units. Yes? Why is it open? Oh, why is A upper 0 open? Ring of definition. Yeah, so you have to trace through what, yeah, so if you have a ring of definition A lower 0, oh yeah, I should say this. Thank you. Thank you. So elements of A lower 0 are going to end up being power bounded in the way you set this up. So A0 is open, and it's a ring, and this whole thing is linearly topologized, so that means that this A upper 0 is open. Okay. All right, and, oh, yeah, why else are uniform Tate rings quite nice? Well, they are Banach algebras. Yes?
Were you not stating that the power-bounded elements were the ring of definition for uniform Tate rings?
No. Yes, it's confusing because one is notated with A lower 0, and the other is A upper 0. But if you've never seen these things before, it's okay to confuse these things. For almost all cases, A upper 0 can be a ring of definition. Okay. So, this is all good. And, oh, yeah. Such an A is going to have the structure of a Banach algebra. So the topology on A is generated by this nice norm, if you are uniform and Tate. So some of your intuitions, if you've ever studied Banach algebras, can come into play. Where does this Banach algebra come from? So where does the norm come from? So for A and A, you can go ahead and define it. Oh, I don't know. So is this something that works? 2 to the inf among all integers n, such that your pseudo-uniformizer to the nth power times A brings you into something which is bounded like this. Okay, I hope I got that right. So this is going to be a norm. If the absolute value of A is 0, and this is true for all n, then A actually has to be the 0 element because of the condition that A is uniform. So, And so you have a pseudo-uniformizer, so this is actually going to make sense even when n is negative. So even to state this, you need both properties. Okay. This is page 4. Okay, so we did the rings. The rings are going to be Huber rings. I have to define for each such thing a topological space, and those will serve as our model spaces for the category of Adic spaces. And so these topological spaces are called continuous valuations, spaces of continuous valuations. Okay, and these are modeled on, obviously, QP has an absolute value like this, which defines the topology. QP is complete with respect to that topology, right? So here's the definition. For a Huber ring A, a continuous valuation well, it's a function, which I might write as an absolute value like this, A, and, well, the codomain of this absolute value, this continuous valuation, I'm going to write it this way. It's gamma union 0, where this gamma is a totally ordered abelian group. And, for instance, positive reals are a nice, totally ordered abelian group. And when I throw in 0, I get some kind of monoid, right? 0 ruins it being a group. And so I'm writing this multiplicatively. The identity is going to be 1, and 1 should have absolute value 1. But also 0 should have absolute value 0. So list of things satisfies this, is that it be multiplicative. It should have the non-Archimedean property, right? Sum of two elements. So, yeah, the usual metric on the real numbers is not going to work because it doesn't satisfy this. And the absolute value of 1 should be 1, the identity of this group. And the absolute value of 0 should be 0. And the final condition is a continuity condition. And what does continuity mean? Well, you can put a topology on any such, the order topology on this, extend it to this, and just demand that this be continuous. That works out to be something like, for all gamma and gamma, subset bounded by gamma is open in A. So this is the continuity condition. And this makes a lot of sense, and if you've ever studied Berkovich spaces, you study things like this. These are sometimes called multiplicative semi-norms. Why are they multiplicative? Obviously, because they satisfy this condition. Why are they semi-norms? Well, in a norm, if the absolute value is 0, you'd better be 0. It induces a metric. These are not required to have that property. There may be a kernel to a continuous valuation. And there's a departure from the world of Berkovich spaces. Those absolute values have to be real valued, but we're allowing something rather general here. So what's another example of a totally ordered abelian group? Well, there's any subgroup of that, but that's not too different. Something truly different might be a product of two of these guys. course, there's many things you can do along those lines. This is really truly different. How do you order this? You use the lexicographical ordering. You first look at the first term, compare those. If those are equal, then you look at the second term. And then you get this rank 2 valuation, which has, you can think of it as the real numbers, but then between 1 and everything less than 1, there's a whole real numbers worth of other real numbers inside. So there's kind of 2 levels of ordering on such a thing, and the thing is rank 2. And this makes Adic spaces rather different than Berkovich spaces. Okay. So I need a notion of equivalence for these guys. I say that one absolute value and another absolute value are equivalent if, well, they induce the same comparisons on all elements of the Huber ring A. Fair enough. That makes sense. And you can recast this in some other way. You could maybe make this gamma small enough, the smallest possible thing which contains the image of that, and then demand that when you do that to both these guys, this one and this one, if the 2 value groups are the same. Other ways of recasting this. Okay. All right, well, we're ready to talk about what topological space is attached to a Huber ring A, and it's going to work like this. I'm going to define continuous of A, cont of A, to be the set of equivalence classes of continuous valuations. On A. Great. And that's a set, of course. I need to talk about what the topology is. I will sum it up this way. The topology is going to be generated by sets of this form. Oh, I didn't. Oh, yeah, okay. Oh, I need a. Sorry. Strange notation here. I'm going to label points of the set as X because we like points of sets to be labeled as X. And then when I have an element F in the ring, I'm going to use this thing to mean the absolute value of X with respect to the continuous valuation labeled by X. And this is a natural kind of shift. I mean, the elements of a ring should be considered as functions on the spectrum or the spum or the whatever we put on it, and also this cont in this way. Okay. So the topology is generated by subsets of this form. You want an inequality to hold where this g of x is not equal to 0. Okay. So this means that there's this means the set of all x inside of cont of A such that this is true, such that the absolute value labeled by x thinks that f is less than or equal to g and that g is not 0. Okay. So if I didn't have the f here, this would be everything where g is non-zero. And indeed, I can always just let f be 0, and these things are going to be open. And that's something like the Zariski topology on a scheme. And so this captures elements of a Zariski topology. I can also do things like, well, inside of the rigid disk, I can make t be less than or equal to p and get a subdisk of radius 1 over p and do analytic things like this. I can make this be some power of p and get basically epsilon neighborhoods. So what I'm saying here is this is going to blend aspects of the Zariski topology and an analytic topology. It's rather flexible. Okay. And that is 5. Oh, we better do some examples of this. So, okay, this is a basic example. A finite field. What are the continuous valuations on a finite field? Well, there's a trivial one, which I might call absolute value sum 0, which just assigns 0 to 0 and 1 to everything else. Well, guess what? That's the only one. Why? Well, any non-zero element is a root of unity, and because this is multiplicative, it has to assign 1 to that as well. Okay. Not very interesting. The same is true for any algebraic extension of FP. Great. Cont of QP. Okay. Well, there's the usual p-adic absolute value, which I might write that, right? And could there be anything else? Well, there's this element p, which is a topologically nilpotent unit. So p has to go to something non-zero, but also something less than 1. And so you see that tension there. And in fact, once you've determined where p goes, that forces your hand with everything else. It has to be continuous. So powers of p get sent where they like, and then p-adic units actually have to get sent to 1. Like if you've, well, that maybe you won't give away that exercise, but p-adic units have to go to 1 in such a thing because of the continuity, and also because those are units. You can find some sequence of powers which goes to 1. So that's all there is. And if you did this with a ZP, well, you would find that there are 2 points, S and eta. S and eta. And S is going to be the special point, right? So ZP maps to FP. And I can then do a trivial absolute value to the set 0, 1. And that composition is going to be called S. That's the special point. And then there's this generic point, which is a ZP maps to QP, and then absolute value P goes to positive non-negative reals, right? So those are the 2 points. It turns out those are the only 2. So now we have a 2-point set, and it's a topological space. What's the topology on it? Well, this is one of those things called a trait. The eta, the closure of eta is everything. So in fact, this eta is, I can write it as an open subset in this sense. It's everything where p is not 0. If I have an element of Kant ZP, and it thinks that p is not equal to 0, it turns out that that has to be just this eta. So in fact, eta is an open subset. Eta is an open subset of Kant ZP. And the closure is everything. And this is closed because its complement is open. So there you have everything you need to know about the topology on this set. Okay. All right, well, those are very easy examples, weren't they? Next one would be Kant of QP angle brackets T, right? Okay. So what is this? Well, one thing I can say is that there is a map from the rigid space SPM of QPT into this space. So the continuous valuation space contains this maximal spectrum. Why is that the case? Well, if I have some maximal ideal M, then from the theory of Tate algebras, the quotient QPT modulo M is some finite extension of QP. It's a p-adic field. And so I can just send this to the valuation pulled back from that. Right? Okay. So I get an equivalence class of valuations for every maximal ideal here. But this latter space contains many, many, many more points. So I'm going to give you an example of such a point. So here's a point in here which is not in here, and it's going to use a higher rank valuation. So let's let gamma. So this contains more points. So let's let gamma be. So it'll be an ordered abelian group of rank 2. It'll be the positive reals cross some cyclic abelian group. And what's the order on this? I have to tell you where gamma lies in all of this. Gamma is going to be less than the real number 1, but it's going to be greater than every real number less than 1. And that determines what the order type of this thing is. Okay. And what the valuation is, I'm going to say that we have this element x minus. Okay. And x minus is going to do the following things. So the absolute value of a power series according to x minus is going to be, well, it'll be this formula. So sup of an under the usual absolute value, which is real valued, times gamma to the n. Which is some formula. But in particular, the absolute value of t is going to be gamma. So this absolute value, x minus, it thinks that t is slightly less than 1, but bigger than all real numbers which are less than 1. And this distinction actually matters a lot. This is what prevents you from disconnecting the rigid disk into two pieces, the outer circle and everything in between. So if I were to do something like this, so here's the thing. I can make a... I told you what the topology on this set was. It's generated by open sets of this form, where you compare two elements like this. Oh, and p is not equal to 0 because this thing contains qp and p is a unit, so there's no need to write p not equal to 0. And I can take the union of all of these guys, right? And so this is kind of telling you that t is less than or equal to p to the 1 over n for all n, which is kind of telling you that t is less than 1. And so you might think that this, together with this outer circle, which is also an open subset of the same form if you think hard enough, these do not cover cont of qp angle brackets t, because neither contains x minus. So because of x minus. Okay, x minus does not belong to any of these things, because x minus thinks that none of these are true. T is going to be larger than any power of p to the 1 over n, but it's still less than 1, so it's not here either. Okay. This topological space cont of qp angle brackets t, so it contains many points of rank 2. There's many variations on that idea. I can also flip the minus to a plus. Where gamma is greater than 1. That is, I could flip the sign of gamma from being less than 1 to being greater than 1, but just barely, so that this absolute value, x upper plus, will think that t is slightly larger than 1. And so I'm thinking about x plus and x minus as elements of this topological space, which are slightly within a disk and slightly without of the disk. I need to revise the theory a little bit to exclude elements like this x plus. The thing is, I would like to be able to define a closed unit disk, everything less than or equal to 1, and that should really exclude the point x plus, which thinks that t is slightly greater than 1. So I need a way to exclude this, and the fix is to include rings of integral elements. So what I do is I say that a plus inside of A is a ring of integral elements. If it's open, integrally closed. Okay. And, oh, excuse me. All right, so it's going to be a subring of A contained in A upper circ, so elements of it should be power bounded. All right, it can't be the whole thing in most cases. And then I'm going to trim this set cont of A by using this A upper plus, and I define spa, so this is the first instance of this. Okay, so this is going to be everything inside of cont of A that thinks that elements of A plus are less than or equal to 1. Okay. So, as an example, if A is our Tate algebra over QP in one variable, I could have A plus be, well, this one. Yeah. So that, in that case, it's just A circ. Yeah. And then you get all the elements that think that T is less than or equal to 1. So you exclude this x upper plus thing. Although it does contain x upper minus and all the rest. Yeah. I could do another thing along these lines, though. I could actually come up with a smaller ring of integral elements which does not contain t. How would I do that? All right, so I notated this in the notes as a plus plus, so it's a smaller ring. So it's going to be all of the power series where, well, the A0 can be in ZP, but all of the rest of them have to be in PZP. Yeah. This does not contain t. It contains p times t. It contains p times t squared and all of that. But it does not contain t. And in fact, this thing, this A double plus is kind of the biggest you can make it. This is all of cont of A. Yeah, if you think about it. Any absolute value inside of cont of A is going to think that any element of this is less than or equal to 1. Because p times t is going to have to be less than 1. It's topologically nilpotent. Okay. Okay. So far, so good. I have no time at all. No. Okay, yeah, that's okay. I'm just gonna, that's okay. I'll just push it into the next lecture. That's all right. And so I'll just, I'll just conclude by saying that SPA QP angle brackets T, ZP angle brackets T, this is the Adic closed unit disk. Call it X. And next time we'll be talking about the structure sheaf, or generally the structure pre-sheaf on a SPA of an A plus like this. And then I will be able to define the class of Adic spaces. Thank you.
Questions for Jared? Wait.
What was the asterisk on schemes?
I didn't get to the asterisk on schemes. I'll talk about it tomorrow. But if you're, it has to do with this structure pre-sheaf being a sheaf. And I'm not, in the absence of Noetherian hypotheses. What? If the ring is discrete, everything is okay? Oh, wonderful. Okay, so actually, the asterisk, if you looked closely enough, was only, yeah. So, the trouble is with, The trouble is if you have a general A, or a general pair A plus, the structure pre-sheaf won't be a sheaf, and you can't create an Adic space out of it. Yeah.
I'll be talking about this next time.
Oh, good. There's a question here.
Yeah, so why do we actually want or need A plus to be integrally closed?
Why do we need the A plus to be integrally closed? I think if you don't, you actually get the same thing as if you made A plus be the integral closure. Is that right? And then by demanding it, it's kind of convenient. It turns out that, there's a nice classification of which A pluses appear. But that classification is only nice if you only allow the integrally closed ones. So,
A plus are bijection in certain subsets of content.
That's right.
Once you close them.
That's right. Oh, the possible A pluses that, given an A, the possible A pluses that can appear are in bijection with certain subsets of cont of A. And that bijection is only valid if you only allow the integrally closed A pluses.
Let's thank Jared again.